This question is about free energy changes, delta G, enthalpy changes, delta H, and temperature, T. Part A. The Gibbs equation is shown below. A chemist investigates a reaction to determine how delta G varies with T. The results are shown in figure 18.1. What is significant about the gradient of the line and the values P and Q shown in figure 18.1? Explain your reasoning. So firstly, let's look at the equation for Gibbs free energy. If we rewrite this equation, we can easily compare it to the equation for a straight line. The equation for a straight line is y equals mx plus c. So I've written what it corresponds to underneath the equation for Gibbs free energy. Therefore, we can extrapolate what the gradient means. So, gradient of the line is change in y over change in x, and that would be minus delta s. Looking at the equation, the minus and the delta s comes from here. Then P, well, P is the y-intercept, or C, and that is delta H, or the enthalpy changes. And Q is the T from the equation, the other bit. And we need to specify here, though, it's the temperature at which feasibility changes. And this is very important because that's what Gibbs free energy is all about. It's about feasibility of reactions. To get the 4 marks for this question, you need to compare the equation for Gibbs free energy to the equation of a straight line. You need to say what the gradient is and the values of P and Q. Part B. Iron can be extracted from its ore, Fe3O4, using carbon. Several equilibria are involved using equilibrium 18.1 shown below. Part 1. Why is equilibrium 18.1 a heterogeneous equilibrium? So this is quite a common question where they ask you about heterogeneous and homogeneous equilibrium. Heterogeneous means that the reactants and products are in different states. To get the mark for this part of the question, you just need to write that they're in different states or phases. Part 2, write the expression for Kp for equilibrium 18.1. When writing the expression for Kp, we need to look at the reactants or products in a gaseous state. Carbon monoxide is the only reactant or product in a gaseous state. So when writing an expression for Kp, we use carbon monoxide, we write P, CO, G, and then the stoichiometry, or the big number in front of carbon monoxide, in this case 4, is what we raise the power to. So we would raise the carbon monoxide to the power of 4. To get the mark for this question, you need to write Kp equals P, CO, gaseous, to the power of 4. Part 3. The forward reaction in equilibrium 18.1 is only feasible at high temperatures. 1. Show that the forward reaction is not feasible at 25 degrees Celsius. And 2. Calculate the minimum temperature in Kelvin for the forward reaction to be feasible. Let's begin answering this question by writing the equation for Gibbs free energy. And that is delta G equals delta H minus delta S T. So if we were to plug in the numbers that we're given, we can work out delta G. So we've got 676.4 minus 0.7031, because I have converted the joules K to the minus 1 moles to the minus 1 into kilojoules K to the minus 1 moles to the minus 1. And then we need to multiply by the temperature, and we do that in Kelvin. So it's 298 because to convert 25 degrees Celsius into Kelvin, we need to add 273. That gives us a delta G value of 467 kilojoules per mole, and that means that delta G is bigger than 0, so it's not feasible. That's a key statement we need to write in this question. To work out minimum temperature in Kelvin can be calculated by taking delta H and dividing it by delta S. So that would equal 676.4 divided by 0.7031, which gives us 962 Kelvin. So that's what we would write on our answer line. To get the 3 marks for this question, you need to correctly calculate delta G, so 467. You need to state that it's not feasible because delta G is bigger than 0. And then you need to calculate the minimum temperature correctly and write 962 on the answer line. Part 4. Another equilibrium involved the extraction of iron from Fe3O4 is shown below. Enthalpy changes of formation, delta FH for Fe3O4 solid and CO2 gas are shown in the table. Calculate the enthalpy change of formation, delta FH for carbon monoxide or CO gas. To begin this question, let's rewrite the equation because then we can write a Hess's triangle, and that will help us to calculate the enthalpy change of formation of carbon monoxide. We have the enthalpy changes of formations of Fe3O4, so we can add that into our Hess's triangle. It's minus 1118.5. We don't know carbon monoxide, so that'll be 4x. Iron, that's 0 because it's already formed in its basic state. And CO2 is 4 times minus 393.5. I know these values from our table that we've been given. We can then write our delta H for the overall equation over the arrow, so minus 13.5. The way a Hess's triangle works is you want to go round from the products to the reactants. This is not the simplest way. The simplest way is this arrow here, but we need to work out the enthalpy change of formation, so we do that by working from reactants to products. So we want the arrow to go this way, and we do this. We can write plus 1118.5 minus 4x in brackets plus 0 plus 4 times minus 393.5 equals minus 13.5. If we rearrange this equation, we can get 1118.5 minus 4x equals 1560.5. Continuing to rearrange, we get that minus 4x equals 442. So x equals minus 110.5, and that's what we write in our answer space. To get the 3 marks for this question, you get a mark for the first bit of the equation, putting all of your enthalpy changes in the correct format and making it equal the delta H, a mark for rearranging, and a mark for x.